and anything which is an element of F is called the event. Okay. So anything which is an element of F is called the event. And you always define probability for events, right? I mean, just like that day we are discussing many examples like tossing a coin or throwing a die. Anything, whatever you do, you always define, try, you look for the probability of an event. Okay, so it's like you are always looking for probability which is an event. Okay, so I mean, if something is not an event, you cannot have. I mean, you don't define the probability functions over there. So what is a probability measure, right? So probability measure is uh, is so we'll define okay. So let's define what is a probability measure. The probability measure is a so you have omega and you have F, the sigma algebra defined. Okay. So this is this thing omega and F, and this yeah this I think this this tuple is called it's called has a name. So what's the name of this thing? So uh, anyway, so you take omega, and with omega you consider the sigma algebra over what is a probability measure? So what is a probability measure is nothing. So it's a function. So probability measure is a function. Okay? So it's a real valued function. Uh, Real valued function over 0, 1. So it maps in the 0, 1 interval. Right? It's not over the whole R. It is it's uh, it's over 0, 1. Okay. So it's a function. It's a function which so therefore you so what are we looking for? We are trying to look for probability of an event of the A, right? So you take an element of the F, and the probability of that is always between 0 to 1, right? Probability measure is it's a function between 0 to 1 such that okay, so probability of the whole set is 1, or probability of the similarly if your probability of the empty set is 0, right? Because it's valid, it can takes maximum value 1, minimum 0, so it's this thing. Okay. Mm. And and so this is the one property, and then this if These are pairwise disjoint. So pairwise disjoint means what? That AI intersection AJ is equal to null set for I not equal to J. So that means it's a pairwise disjoint. So each of the thing is pairwise disjoint. Uh, so if AI these are pairwise disjoint sets uh, belonging to F. So all AIs belongs to F. Then probability of union of AI, okay, I belongs to natural number is equal to summation. So so you see, this is the countable collection, right? So this is countable. It is not saying the finiteness. So probability measured is something which satisfies these two properties. So it has to, so it's a real valued function from sigma algebra to 0, 1. It takes values from sigma algebra, maps to 0, 1 interval. And if you have a pairwise sequence of pairwise disjoint sets, then probability of union of AI is equal to summation probability of AI, I equal to. And this three, then these three things, omega, F, and P, all together, this triplet is called probability space. So this triplet together is called a probability space. So what is a probability measure? It's a real valued function from the sigma field to the 0, 1 interval. It satisfies two properties. That is, probability of one set is equal to 1. And if you take a sequence of disjoint, pairwise disjoint sets, then probability of union of AI is equal to summation of probability of I belongs to n matrix. And and this omega fp is called the probability space. And yes, and suppose for any event, I mean if for any event A, if probability of A is equal to 1, this means that so what does it mean? It means that the event uh, A occurs almost sure. This means this A occurs almost sure. So this is some sort of definition or something that for A equal to 1, that means that uh, it means that that means that event is occurring almost surely. Now almost surely it is sense because there is a notion of set of measure 0. Okay? So that means, I mean, for some point it may not happen. I mean, so A is an element of F, right? Sigma algebra. Just a minute. Hello. So the event A occurs almost sure. So so it's a it's an almost sure definition. So that something probability equal to one. That means that the event occurs almost sure. Uh, and then we have defined the R, BR over these things. So, for example, we were discussing something about choosing a point from an interval, right? So so even one, I mean, example is like if you take omega is equal to 0, 1, and you can always have the sigma field is the Borel sigma field over 0, 1, right? And and you can have the Lebesgue measure, Lebesgue, and uh, so this Lebesgue measure is uh, I mean, so we have defined what is Lebesgue measure last time of AB is nothing but D minus. And this Lebesgue measure you can define as this Lebesgue measure is basically uniquely defined uh, over Borel sets. I mean, what is unique? Why? So this measure can be uniquely defined now. How unique? What unique? So those things we may omit for the time being. I'm not will enter so much to the measure theory, but just for your knowledge that so you can have a Lebesgue measure. Last time we have discussed Lebesgue measure over R. So similarly, you can have 0, 1 interval, and you can define a Borel Borel sets over 0, 1, Borel sigma algebra over it, and then Lebesgue measure we can define on 0, 1. So like this. Yeah, I mean, basically you can construct a probability space like Borel's one. So here it is the collection of all intervals between 0, 1. Right? We have discussed about R, PR, and P. So here it is. I mean, instead of the whole R, you consider the 0, 1 interval R. And we know the cardinality of any interval is equal to the cardinality of the whole R. Um, so there are important this thing. So there are some properties. So suppose you have increasing sequence of sets. Okay. So as well. So you have increasing sequence of sets. Then So if you have increasing sequence of sets, then this is going to uh, uh, this will be the, so this is called some sort of continuity property or something of the probability measure. So if you have now, so what you have an increasing sequence of sets. So let's discuss the proof. So you have an increasing sequence of sets, right? So A1 is a subset of A2 is a subset of A3. So what does it, how the picture will look like? So it is like A1, you have A2, you have A3. So this way it goes on, right? I mean, you have something here, AN. So correct, correct. It's an increasing sequence of sets, right? Uh, now, now I can prove it by the, so what we know till now, we know till now that these two property, I mean, what is a probability measure? Probability measure is a real value function which satisfies these two properties. For disjoint, the union is equal to summation of these things. Okay, so definitely I have to use these two properties only to prove this. Uh, so okay, uh, so it's like, so I have this area is A1, right? And for A2 is the whole thing, right? Right. So I have certain intersection here. So these are not disjoint. Right? Similarly, for A3, it is the this area. So A3 has some intersection with A2 and A1. But if I want to use the definition of the probability measure, it's the pairwise disjoints, right? I need so what we can do, we can do something like, so I can define, so B1, A1, so we can define B1 as B2 is defined as A2, correct? Then B3, I defined as A3 minus A2. So this way, I can have BI defined as AI minus. So therefore now what I have, I have like, so I have this one is B1, then I have this area is B2, right? I have this area is B3, correct? This strip, the outside strip is B3, and here I have outside the BI. So, so in a sense, so my so this thing is B1. This whole thing out, so this strip is B2. Here I have B3, and this way. So these BIs are in. disjoint, right? The way I have defined BI A1, A2, A3, so this so B1, B2, B3. So BIs are disjoint, correct? Right? Correct?
Yes, sir.
Yes, sir.
So what I have is the BIs are disjoint, right? Now, now you notice one thing is, is now you notice one thing. What about B1, B2, B? Suppose just take B1. What is this field? What is B1 union B2? Anyone?
A2, sir.
Yeah. So B1. So this is A2. B1 union B2 union B3 is nothing but A3. So you can do B1 union B2, and I have B1 equal to A1. Let's try to. So these are disjoint unions, right? BI is a disjoint union, right? So what I have in the left side, I have this probability of union of n, uh, this thing. So what I can write now? So what is an? What is an?
B1 union B2
Hmm.
from B.
Correct. So this is n equal to, I mean, n belongs to n means n equal to 1 to infinity, and k equal to 1 to n. So, so this is, I mean, this is both union, right? This is nothing but both the union. So this is probability of union, right? Or we can write it something. So just to we can write it as, so this is k equal to 1 to n and n equal to 1 to infinity, right? So in a sense that this is nothing but limit n goes to infinity. Correct? Is this step clear?
Yes, sir.
And what about this fellow? This is nothing but is an.
AN.
Okay. So this is proof, right? This is what I want to prove. So yeah, so in a sense that this is also called the continuity of the, so this property of probability measure is also called the continuity of probability. We have another property which is called the continuity from above. And Yeah. So continuity from above. So this is like if you have so 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 A1, A2, like the same thing. So you have this thing is belongs to F. So this one also, I mean, these are sequence. Sorry, these are sequence which belongs to F. So this is a so this thing such that you have A1, A2, A3. So you have a decreasing sequence of steps, right? You have a decreasing sequence of steps. Then probability of intersection of n goes to n. A n is limit n goes to n. So now you have a decreasing sequence. So in a sense that you have A2 is contained in A1, A3 is contained. So in a sense that this is your A1. Then you have A2. Then you have A3. So you have A1. So now you have a decreasing sequence of steps. And you have to show that this is now how will you do it? Any idea? Any idea? Anyone?
Sir, can we do just by intersection?
Sorry,
A1 intersection.
again repeat.
By doing intersection. A1 intersection A2 is A2, A2 intersection A3 is A3.
Yeah, we have to do something like that, but we have to use. I mean, what we have. What are the things we know? We know the disjoint additivity, and we have proved the continuity from above. These are the two things we know. We have to use that. I mean, look. So, what about this A intersection B complement? What is that? Anyone? De Morgan's law? What is A intersection B complement? A intersection B complement? What is, suppose this is my omega, this is my A, this is my B. What is my A intersection B? This is A intersection B, right? Correct? So A intersection B complement is what?
Sir, A
But
complement union B complement.
exactly. So my A complement is this one, right? This is my A complement, and my B complement is this one. Right? So so A intersection B complement is nothing but A complement union B complement. Correct? Yeah. And suppose another property I would just say, and then suppose if A is a subset of B, A is a subset of B, right? So that means how does it look like? So A and then B, right? A is a subset of B means this. Now, what about the A complement and B complement? So my A complement is this one, and B complement is this one. Correct? So if A is a subset of B, then B complement is a subset of A complement, right? Correct? From the picture, is it clear? Hello? Hello?
Yes, sir.
So if A is a subset of B, then B complement is a subset of A complement. So if you take naturally, so if you consider A1 intersection A2 intersection or something complement, so you can, so it will be A1 complement union A2 complement, sorry, complement union A3 complement union dot, dot, dot. So A1 A2 is a decreasing sequence of sets, but this complement is again will be the increasing sequence of sets, right? This is an increasing sequence of sets. Correct. And then you use the first result because this is an increasing sequence of sets. And then you use the first result, and you can get the result. So yeah, you try this. Okay. This is so you have to use the first lemma to get this result, and you have to use De Morgan's law. And this if A is a subset of B, the complement is a subset of A complement. So, and then this is an increasing sequence of sets, and you use the first lemma, you get the result. Okay, we stop it here today. ठीक है? Okay.
Yes, sir.